Reliability. The theory of reliability is the analysis of failures of systems that are operating, their causes and within predetermined limits under given operating conditions. Any complex systems, even if properly designed, they are prone to failure. Study of failure properties of a component of a system is most important characteristics of the product quality, as things have to be working satisfactorily before considering their quality attributes. Reliability is an internal property of operating system, and as such it has to be specified as a part of the system's characteristics. Hence, it is necessary to develop quantitative systems to measure their reliability as accurately as possible. This enables one to compare performance of similar systems on a reliability basis and develop methods for improving reliability of a particular system. Here, we discuss the statistical basis of theory of reliability and assume the reader is familiar with various probability distribution functions of random variables. Usually, specific performance measures can be embedded into reliability analysis by the fact that if the performance is below certain level, a failure can be said to have occurred. The term reliability is used generally to express a certain degree of assurance that a device of a system will operate successfully in the specific environment during a certain time period. The concept is a dynamic one and does not refer just to an instantaneous event. If the device fails, this does not necessarily imply that it is unreliable. Every piece of mechanical or electronic component fails once in a while. The question is, however, how frequently failures occur in a specified time period. These are often some confusion among the practitioners between quality level and reliability. It is the proportion of defective computer chips manufactured daily is too high. We would say that the manufacturing process is sufficiently reliable. The defective computer chips are scrapped, yet the non-defective ones may be very reliable. Reliability of a computer chips depends on the technological design and their function in the computer. If the installed chips do not fail frequently, they might be considered reliable. Life distributions. The length of life of a component, which is a random variable, and it is a basis of reliable functions and other related functions. The length of lifetime of components or systems is the length of the time interval t from the initial activation of the unit until its failure. This variable t is considered a random variable since the length of life cannot be exactly predetermined. The probability distribution function of t or cumulative distribution function, which is in short called as a CDF of t, denoted by f of t, is the probability that the lifetime does not exceed t. That is, f of t is equal to probability of t is uppercase t is less than or equal to lowercase t, that is 0 less than or equal to t less than infinity. The lifetime random variable t is called continuous if its CDF is continuous function of t. For such lifetime random variables, the probability density function, in short PDF, corresponds to a f of t is defined by its derivative if it exists, and we denote it PDF by lowercase f of t. This is a non-negative valued function such that f of t is equal to minus infinity to t f of x dx for all minus infinity less than t plus infinity. Since the life distributions are non-negative valued random variable, it can also be written as 0 to t f of x dx for all t greater than or equal to 0. Reliability function. Reliability is the probability that the system will perform its intended function under specified working condition for a specified period of time. Mathematically, reliability function R of t is the probability that the system will be successfully operating without failure in the interval from time 0 to time t. Reliability function can be written in terms of PDF whenever the life distribution function is continuous, and it is given by And also note that hazard function, the failure rate function or hazard function is very important in reliability analysis, because it specifies the rate of the system aging. The definition of failure rate function is given as the hazard function or hazard rate or a failure rate of function lambda t of the system is defined that lambda t dt is the conditional probability of time to failure of the system in the time interval t to t plus dt, given the system has not failed from the origin up to time t for any non-negative t. Thus, lambda t dt is equal to probability t less than t less than t plus dt given t is greater than t, which is equal to probability t less than t less than t plus dt t greater than t divided by probability of t greater than t. The numerator in the right hand side expression is a joint probability that the system has survived to time t and will fail in time interval t to t plus dt. This is equivalent to the probability that the system will fail in time interval t to dt, since this event presumes survival of the system to time t. Hence, lambda of t dt is equal to probability of t less than t divided by probability of t is greater than t. This is equal to f of t dt divided by r of t, and this is equal to lambda of t is equal to limit dt goes to 0 probability of t less than t plus dt divided by dt probability of t greater t. This is equal to, this part is f of t and this is r of t. Lambda of t is equal to limit dt goes to 0 r of t minus r of t plus dt divided by dt and r of t. This can be written as limit dt goes to 0 with minus sign r of t plus dt minus r of t divided by dt r of t equal to f of t r of t. Alternatively, lambda of t is equal to f of t divided by 1 minus f of t for all t greater than equal to 0. Suppose that we have a large number of identical components which start operating at exactly the same time under identical conditions, then lambda t dt denotes the proportion of components that have survived up to time t, but will fail in the interval t to t plus dt. Following expressions for distribution function, reliability function and density function are given in terms of hazard function with an assumption that f of 0, that is distribution function at 0, is 0. With f of 0 is equal to 0, we have the following relations. The distribution function is written in terms of and the reliability function r of t is equal to Now, the density function f of t can be obtained by differentiating this function with respect to x, and we get this as minus and minus cancels, and then lambda of t and this function itself lambda of x dx for all t greater than or equal to 0. Yes. Now, let us discuss some common life distributions. First, exponential distribution. The simplest form of hazard function is constant. That means, it is constant for every t. Lambda of t is equal to lambda for all t non-negative. Then f of t, using the expression obtained earlier, we get minus 0 to t lambda dx, and this is equal to lambda minus lambda t for all t greater than or equal to 0. Yes. This is the exponential density function, that is, lifetime is exponential distribution. The mean of this lifetime distribution is 1 divided by lambda. Consider an example. A particular component is a complex mechanical system, has an exponential time to failure, or lifetime distribution with mean time to failure is 1000 hours. Then A, the density function or PDF of the time to failure of f t is equal to lambda exponential of minus lambda t, where lambda is positive, t is positive. That is, lambda is 1 divided by 1000, which is equal to 0.001. The reliability function r of t is equal to exponential of minus lambda t, and it is equal to exponential of minus 0.001 times t for all non-negative t. C, if the component has to operate for 2000 hours, its reliability, which is the probability of survival after 2000 hours of operation, is r of 2000, that is equal to exponential of minus 0.001 multiplied by 2000, that is equal to exponential function of minus 2, and that is equal to 0.1352. This is the probability of survival beyond 2000 hours. In case of exponential life distribution, it is true that if a unit is functioning at time t and the probability of survival or additional time t a is the same as earlier, that is, regardless of time, probability of t greater than t plus t a given t is greater than t is equal to probability of t greater than t plus t a and intersect with the t is greater than t divided by probability of t is greater than t. This is same as by taking the intersection probability of t is greater than t plus t a divided by probability of t is greater than t. Using the reliability function, this is exponential minus lambda t plus t a divided by exponential minus lambda t. This simplifies to exponential minus lambda t a, and that is equal to r of t a. Weibull distribution. This is frequently used to model fatigue failure, ball bearing failure, etc. These have very long tails. The probability density function or PDF is given by f of t is equal to lambda alpha t power alpha minus 1 exponential minus lambda t alpha for t greater than or equal to 0. And the distribution function is given by f of t is equal to 1 minus exponential minus lambda t power alpha for all t greater than or equal to 0, and the reliability function r of t is exponential minus lambda t alpha for all t greater than or equal to 0. The hazard function h of t is given by lambda alpha t power alpha minus 1 for all t greater than or equal to 0. This is a 2-parameter Weibull distributions. Alpha is called the shape parameter and lambda is the scale parameter. This reduces to exponential distribution when alpha is equal to 1. We note that for the Weibull distribution, the hazard function is decreasing if 0 less than alpha less than 1, constant if alpha is equal to 1, increasing if alpha is greater than 1. Hence, Weibull distribution is capable of modeling decreasing failure rate, that is when alpha is less than 1, constant failure rate when alpha is equal to 1, and increasing failure rate when alpha is greater than 1. This class of hazard function provides a practical means for fitting the various portions of life characteristic curve of system. The initial failure portion would be represented by hazard function with alpha less than 1. The random failure portion would be represented to hazard function alpha with alpha is equal to 1, and wear out failure portion would be represented by hazard function with alpha greater than 1. Discrete distributions are also used to model distributions in reliability. Binomial distribution is one of the most widely used discrete random variable in reliability and quality inspection. It has applications in reliability engineering, that is when one of the dealings with the situation in which an event is either a success or a failure. Although the Poisson distribution can be used in a manner similar to the binomial distribution, it is used to deal with the events in which the sample size is unknown. Reliability of a series system. A system consists of 4 components in series, each having probabilities as indicated here. That is, first one is with probability 0.97, second one with the reliability of 0.95, third with the reliability of 0.98, fourth one is with the reliability of 0.99. What is the reliability of the system? Now, the reliability of the system is the product of all these reliability as indicated earlier, and that is 0.97 multiplied by 0.95 multiplied by 0.98 multiplied by 0.99, and this product is 0.894093. Suppose the system consists of 8 components in series, each is having a reliability of 0.98, then the reliability of the system is 0.98 to the power 8, and that is equal to 0.850763. An electronic product containing 100 integrated circuits, the probability that any integrated circuit is defective is 0.001, and integrated circuits are independent. With these conditions, the product operates only if all the integrated circuits are operational. Then what is the probability that the product is operational? Solution. The probability that any component is functioning is 0.999. Since the product operates only if all 100 components are operational, the probability that 100 components are functioning is 0.999 to the power 100, which is equal to 0.904792. The reliability is just over 90%. Even though each component has a reliability of 99.9%. Reliability of a parallel system. Parallel system works only if all its components fail. For example, if an office has n copy machines, it is possible to copy a document if at least one machine is good working conditions. The system fails only when all components fail. Hence, the probability of failure of a parallel system is the product of probability of the failure of all individual components. If P1, P2, etc. Pn are reliability of individual components, then the reliability of the system is given by 1 minus P1 multiplied by 1 minus P2 multiplied by 1 minus P3 etc. 1 minus Pn. The configuration of the system is as shown in the figure. They are connected parallelly. Examples: a system consists of 4 components in parallel. If reliability of these components are 0.9, 0.85, 0.8, 0.9 respectively, then overall reliability of the system is 1 minus 0.1 multiplied by 0.15 multiplied by 0.2 multiplied by 0.1, that is equal to 0.9997, that is 99.97%. A system has 3 components and probabilities of failure of these components are 0.05, 0.1, 0.15 respectively. What is the probability that system is reliable? The system reliability is 1 minus 0.05 multiplied by 0.1 multiplied by 0.15, and the answer is 0.99925. Practicals. For example, for all positive t, following expressions hold for 3 distributions. The density functions, distribution function, reliability functions and hazard functions are given for exponential and variable distributions in columns. Now, for exponential distribution, density function is lambda multiplied by exponential of minus lambda t, and distribution function 1 minus exponential of minus lambda t, reliability function is exponential of minus lambda t, and hazard function is lambda. Variable distribution, the density function is lambda alpha t power alpha minus 1 exponential of minus lambda t power alpha, and distribution function is 1 minus exponential of minus lambda t power alpha. Reliability function is exponential of minus lambda t power alpha, and hazard function is lambda alpha t power alpha minus 1. Let x have exponential distribution with the different parameters. For lambda is equal to 0.5, for this parameter value, the following table gives various functions: hazard function, reliability function, density function and distribution function over various time values. The time values are 0.1, 0.2, 0.5, 0.7, 1, 1.5, 2, 3, 5 etc. And hazard function, one can observe that it is a constant, whereas reliability function is steadily decreasing from 1 to 0 over these values. The density function is a decreasing function of t. The distribution function is ranging from 0 to 1. From 0 to 1 it is increasing as t increases. A similar feature can be seen even when lambda is equal to 1, where the hazard function is constant, reliability function is decreasing and density function is decreasing, and distribution function is increasing from 0 to 1. Now, again for lambda is equal to 2, we have same time points and hazard function is constant throughout, reliability function is decreasing from 1 to 0, density function can take even values more than 1, but it is again decreasing, distribution function is increasing. The initial value is 0.18, though at 0 the distribution function is 0, it suddenly increases to 0.18 at t is equal to 0.1 and then keeps on increasing until it reaches 1. The graph explains various properties of these functions. Now, let us discuss variable distribution. The parameter is 0.8 for lambda and 1.5 for alpha. For these parameter values, we have again taken time points 0.1, 0.2, 0.5, 0.7, 1, 1.5, 2 and 3. One can take so on, and hazard function is lambda alpha t power alpha minus 1. They are given and we can see that it is increasing function, and when reliability function is a decreasing function from 1 to 0 and density function is increasing function, The distribution function is increasing from 0.1 to infinity. The values shown here shows as increasing until value 3, and various these functions are plotted in the graph. Example on parallel and series system. Each component in the system shown in is operable with probability 0.92 independently of other components. Upper link AB works if both A and B work. Thus, we can replace this link with a component F that operates with probability of A intersection B, that is equal to 0.92 square, that is equal to 0.8464 B. The components D and E connected in parallel can be replaced by component G that operates with the probability of D union E, that is equal to 1 minus of 0.92 whole square, that is equal to 0.9936. Now, C. Now, the configuration can be shown as the component C and G connected in series, so that they can be replaced by a component H that operates with the probability of C intersection G, that is equal to 0.92 multiplied by 0.9936 with the respective probability, and the product is 0.9141. The new configuration can be seen as a parallel as given here. Lastly, the components F and H are in parallel. So, the reliability of the system is probability of F union H, that is equal to 1 minus of 0.8424 multiplied by 1 minus 0.9141, that is equal to 0.9868. Hence, reliability of the given system is 0.9868. Conclusions. We have studied various measures such as hazard function, reliability function, density function and distribution function of lifetime of a component. Relationship among them are also seen. These are functions of time. Further, structure of these functions is different for different life distributions. We have also studied how the reliability of each component contributes to the system reliability depending on the configuration of these components in the system, like parallel and series. We have also learnt how to compute these numerical measurements.